Hello students, in this video we are going to discuss a very important topic, that is motional EMF. Okay, for AHS final examination this is very important. Okay, AHS final examination under Assam Higher Secondary Education Council. Okay, this expression that you need to prove that induced EMF on a conductor which is being moved through a magnetic field B is given by this BLV. Okay, so it was asked in 2025 AHS final examination paper. If you check the papers of previous years, 2025, 2024, 2023, 2020. Okay, so you will find this same question. Okay, so it is a very important question. Okay, from examination point of view. So now let's start. Before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID, OJHALAKHYAJIT123. That's my Insta ID. You can follow me on Insta. So now let's start. So let me show you the papers here. This is question paper of 2025 AHS final exam under Assam Higher Secondary Education Council. Okay, so this question, you see, you are asked to prove this expression E is equal to BLV, motional EMF. Here the diagram is given. So same question was asked in 2024. This is paper cutting of 2024 question paper AHS final exam under Assam Higher Secondary Education Council. Okay, this was asked in 2024 also. Same question, you can see clearly. So it was asked in 2023 also, 2023. Okay, and this was asked in 2020 also, right? Same question. So here you see in this diagram, this magnetic field is given in this direction. That means this is the plane of the frame. This frame, I'm talking about this frame. Here is the conductor which is being moved, and the direction of the magnetic field is perpendicular to this. Okay, if you draw the frame this way, okay, on the page, then the direction of this magnetic field will be out of the page like this. Okay, which can be represented by dot. Okay, that means it is normally coming out of the magnetic field lines normally coming out of the screen of your device. You can consider that way also, or you can consider this way. If you consider the plane of the frame perpendicular to the screen of the device, then this magnetic field is upward and perpendicular to this frame. Okay, you can consider that way also. And similarly, in this question paper here, you see here the magnetic field is given in this direction. That means, so this is the plane of the frame. This frame, I'm talking about this frame, and this is the frame, suppose MSRN, and here is the rod which is being moved. Okay, and the direction of the magnetic field is this, which is perpendicular to the plane of the frame. Okay, so same question. Okay, so now let me write the definition of motional EMF. So what do you mean by motional EMF? Suppose here you see this PQ conductor can be moved this way. Okay, let me consider that over this frame. Okay, over these two arms of the frame. So this is a conducting frame, MSRN. This is a conducting frame, and this arm PQ can be moved. Okay, it can be moved, right? And now let us consider that this arm PQ is being moved towards left with velocity v, and this is the direction of the magnetic field which is perpendicular to this frame. Okay, that means you can say that field lines are passing through this frame in a direction perpendicular to this frame. Okay, right? Hope you have understood this. And due to the motion of this rod or this arm, conducting arm, over these two arms, M, S, and Rn, okay, the flux, magnetic flux through this closed circuit, okay, will be changed, because as you move this through this field lines, through this magnetic field, then this area will be reduced, and due to the decrease in area, the number of lines passing through this frame will be also decrease. Okay, that will be also changed, and due to the change in flux, there will be an induced EMF. Okay, there will be an induced EMF in this rod, and that EMF will be called motional EMF, which is produced due to the motion of this arm, right? So hope you have understood this. Now let me write that definition. So here is the definition. The EMF induced in a conductor when it is moved through a magnetic field is called motional EMF. Okay, that is the definition. So now you see, let us consider this figure. Okay, now you see, so now let us consider the rectangular conductor which is shown in the figure. Okay, where the conductor PQ is being moved towards left, okay, with velocity v over the two arms, over the two arms MS and NR of the frame MSRN. Okay, let me consider that way, and here let me take this is X when at an instant t. Okay, this X will be changed with time because this PQ is being moved towards left, right? And this length RS is suppose L. Okay, let me take that length L. So let RS is equal to L, and RQ, this is equal to X. RQ is equal to X. It varies with time t. Okay, right? Okay, now let me copy this figure and let me take a new slide, pause the video and note these things. Okay, so let me copy this diagram and let me go to new slide. Okay, so here is the figure. Okay, now you see what will be the flux through this area enclosed by this closed loop. So flux through PQRS, flux through PQRS will be given by, so let me write here phi b in order to represent magnetic flux, that is magnetic field into area of this will be L into X, right? L into X. Okay, that is the flux. Now what will be the magnitude of this induced EMF? Magnitude of induced EMF, magnitude of induced EMF, that will be equal to we are taking the magnitude d phi by dt. So sorry, it's supposed to be phi b. Okay, magnetic flux d phi by dt. Right, So this is the magnitude of the induced EMF, and so here this part is constant, B and L is constant. Here X varies with time t, as I have already mentioned. Here X varies with time t. So what we're gonna have, BL dx by dt, and here this dx by dt is nothing but v, right? Okay, if x is a function of t, it varies with time t, then and it this pq, when this pq moves in this direction, then this x changes. Okay, so that's why this velocity will be given by dx by dt. So that will be equal to v, since v is equal to dx by dt, right? So that's why what we can write, that induced EMF is equal to this. This is what we needed to show, right? So hope you have understood this. Now here you see, if you check the question paper of 2020, here let me check this one. So here you see, there is one more part here. A straight conductor of length 0.1 meter moves with speed of 10 meter per second perpendicular to the magnetic field of induction, this. Okay, and calculate the induced EMF and state Lenz's law. So let me solve this problem also. Let me show you how to solve this problem. Okay, so first let me clean this phase to solve this problem. So here you see, this conductor PQ is being moved with a length of this PQ is given, this L is given, this L is given here 0.1 meter, and this is being moved with speed of this V is equal to 10 meter per second. This V is equal to 10 meter per second, and the magnetic field is given 1 Weber per meter square, that means 1 Tesla. Okay, right? So what we have, L is equal to 0.1 meter and B is equal to 1 Tesla or 1 Weber per meter square. Okay, and V is equal to 10 meter per second. These are the information given. Okay, so what is the induced EMF? So we need to calculate the induced EMF. E is equal to, that is given by BLV, that we have already derived now, just now we have derived, right? That 1 into L is L is 0.1 and V is 10 meter per second. Okay, so if we multiply this, so here we need to write volt EMF. So if we multiply this, then what we're going to have, 1 volt, right? So that is the answer. Okay, so next question is next part, one more part is there. State the Lenz's law. State the Lenz's law. So what is the statement of Lenz's law? Let me write the statement here. Okay, Lenz's law, let me write here. Lenz's law states that the polarity of induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux, it opposes to the change in the magnetic flux. Let me write it properly. Magnetic flux that produced it. So what does it mean? Let me explain the meaning. Now you see. So here the EMF is induced in this conductor is due to the change in flux through this loop, right? And this change occurs due to the motion of this PQ, right? So the polarity of EMF induced this conductor will be such that, you know, it produces a current, induced current in this conductor in this way, in the direction such that it opposes the change in magnetic flux. That means here you see the magnetic flux is being changed here due to the motion of this PQ when it is moved towards left. Okay, it may be moved towards right also, but here we are considering that we are moving towards left. So the current induced in this conductor will be such that in the direction such that this magnetic field applied here will exert a force in the opposite direction of its motion. It will oppose the motion because this motion is the cause of the change in magnetic flux, and it opposes the cause of change in magnetic flux. Okay, that is the Lenz's law, right? So we have not completed yet. We have more questions or more PYQs on this chapter, electromagnetic induction. Those will be completed in the next video. So stay connected. See you in the next video. Bye bye.